Hello there, it's every lady's two best friends, Ben
and Jerry. We're here to talk to you guys about
carbon dating. Hey, move your character over to where I am. You see that?
Yeah. What is that? A dead body?
Yeah, I don't remember us killing that though. It must be part of the map.
How long do you think it's been there?
I don't know. But there's one way to find out.
As a representative of Half-Lives, we are going to use this pizza. Now let's say if 3 teenage boys are eating the pizza, then it has a half-life of 5 minutes. Now because the pizza went through a half-life, it will now have half of its original amount. If it goes through another half-life, it will be half the amount that there was before the half-life.
Man, we forgot the Asiago.
Ole Holmes!
One way that we can understand carbon-14 is by using this equation. C is the start, how much carbon-14 was originally in the organism. And we're going to use percents for this equation just to make it simpler. And Y is the finish, how much carbon-14 is left in the organism when we try to observe it. K is the constant, and T is the amount of time or half-life of carbon-14. In this case, that number is 5,730 years, and the start will always be 100%. For the case of doing this equation, we're going to use 25% as our finish. So in order to find out the answer to this equation, we have to work through it one piece at a time. First, we want to get rid of the E by separating it. So we divide both sides by 100 to get 25 over 100 is equal to E to K times T, which would be 5,730. Now, the only way to get rid of E is to put ln before it, because that's the way trig works. Don't ask me why. Really don't ask me why. So with that, we get ln 25 over 100 is equal to K times 5,730. Now, because the number we are finally trying to get at is K, that's the only one we do not know. We have to get it by itself by dividing both sides by 5,730. Now, to write this simply, it would come out, if you were to use it in a calculator, ln 25 over 100, all divided by 5,730. The answer that we get for this will be negative 2.42 times 10 to the negative 4. What can we assume if uranium-125 has a longer half-life than carbon-14?
It'll last longer?
That is correct. Because uranium lasts longer, it can go to date things over millions to almost billions of years old, whereas carbon can only last a couple thousand.
So what kind of things can carbon dating be used for?
Well, any living organism or organic material in general, and it works, you know.
Now, because carbon-14 has a half-life of 5,730 years, you can expect that after that amount of time, half of the original amount of carbon would be in the organism that died. When calculating carbon-14 in age, most likely you would want to use percentages rather than actual numbers. Because using actual numbers would be much harder to focus on, whereas percentages would work for the equations needed in order to solve. When describing carbon-14, you compare it to its ratio to carbon-12. Carbon-12, when absorbed by an organism, remains constant after it dies, whereas carbon-14 begins to dissipate once the organism dies and begins eroding. The amount of carbon-14 will always be rational to the amount of carbon-12 in an organism when it dies. But when an organism dies, that's when it can no longer take in carbon in any form. As an organism lives, it breathes in and takes in the oxygen around us. That oxygen consists of multiple types of carbon. Carbon in its stable form would be counted as carbon-12. The organism takes in the exact same ratio of carbon-12 and carbon-14 throughout its life. When the organism dies, it can no longer take in carbon-12 or carbon-14, but the carbon-12 remains the same regardless of whether it's alive or dead. Carbon-14, once it's dead, begins to dissipate. Because of this, carbon-14 will never fully have the exact amount it had when it died. But because it degrades in such a fashion, we're able to calculate how old an organism is based on how much of its original carbon-14 it has. So say that it has 25% of its original carbon-14. You find out the original carbon-14 number by looking at how much carbon-12 it has. Then, based on that, you know it has 25% of the original carbon-14. In order for it to lose 50%, it goes over 5,730 years. And half of 50% is 25. So you know that it takes 2 half-lives in order to lose that much. 2 half-lives would be 5,730 times 2, which comes out to around 11,460. Because of this, we can tell how old an organism has, or how long an organism has been dead, or organic material has been laid dormant. This cannot, however, extend too much because carbon-14 can only last for so long. Otherwise, you have to use other forms of radiation dating, radioactive dating, to tell how old an organism was when it died, or to tell how long it's been buried. We can assume, based on the fact that carbon-14 has a very short half-life compared to other elements, that its entirety does not last very long. That's why other elements are needed to date things that go farther back than carbon can. Carbon in and of itself can accurately date up to 60,000 years. Theoretically, it could date up to 100,000 years. But most scientists don't try to push that. That is why when scientists try to date things older than 100,000 years old, or things that they cannot really possibly know how long it is based on the organisms or the things that are going on around them, they use other type of elements in order to distinguish how long it's been.
As soon as an organism dies, it stops retaining carbon in any form. The longer it's been dead, the harder it will be to determine the date of its death.
But if an organism's been dead for too long, then it becomes impossible to date it using carbon, especially if it's been buried under sedimentary rock.
Well, that's the thing. They won't be able to use carbon to date it, but if the sedimentary rock contains other radioactive isotopes, they'll be able to date it based on those rocks.
So that's all we have to talk about today.
About carbon and radioactive dating.
Thanks for watching. I'm dreaming of a white Christmas, just like the ones I